Hi, my name is Kevin Drinkall and I'm the EMEA Wireless and Cloud Market Development Manager for Zyxel Communications. Today we're going to talk about 802.11ax, high efficiency wireless LAN, about some of the problems that we have in wireless today and how 802.11ax will try and address them. So why is 802.11ax needed? It just seems like we've only just completed installing 802.11ac or even Wave 2 networks, and we're already talking about 802.11ax. But there is a real need for AX. Today's Wi-Fi has inherent limitations that we really need to overcome. So to start with, wireless today is only really able to transmit to a single client per channel. And this is due to its collision avoidance, its backoffs and duration values, which if you're already working Wi-Fi today, then you're probably already aware of. Even the modulation is dictated by the slowest connected device, meaning that you lose any kind of benefit from any new technology that an access point could probably provide when using older generation devices. We have a limited number of channels, certainly in 2.4 gigahertz, where we have only the ability to have 3 non-overlapping channels, as well as having to contend with thousands of non-compliant Wi-Fi devices like microwave or Bluetooth, just as a few examples. The picture looks much better for 5 gigahertz. We have more channels, they are much wider, and technically we have better throughput. But not every channel is available in every region, and you still have to deal with co-channel interference, which is on an increase. And yes, even non-Wi-Fi sources exist in 5 gigahertz, for example, Doppler radar, where the standard physically either waits for 10 minutes or stops you from using the channel if equipment is found in the DFS range. Network density and traffic requirements is on an increase, and it's fast growing as well. Almost everyone and everything wants to be networked. We used to talk about user density when we assumed that we were talking about one user and one device. And then the term quickly became device density as we realized that users are carrying multiple devices. Depending on which research paper you read, the numbers vary between 20 billion and 30 billion connected things by 2020. So the problem is not really going away anytime soon. The problem is no longer about coverage or users or even the devices. It suddenly becomes all about airtime and how you can provide those devices and the applications they are using with the bandwidth they require to function. I mean, think about it. Who really wants to be tied to a desk via a cable? Our working environment has evolved. We are adding more and more devices that enrich our working environment, as well as our personal spaces that demand the connectivity, and they just keep increasing. There's far more contention in Wi-Fi than people think. People want to believe that 802.11ax addresses this by using uplink resource scheduling versus contention. That's definitely going to help, and we certainly will be touching on this in this presentation. So lastly, the 802.11 protocol itself has a lot of overhead just to make the whole thing function, which creates some efficiencies itself. Currently, we have to work around these inefficiencies until we have more spectrum, and there's always an ongoing debate about extending the spectrum and frequencies available to wireless in the US and in Europe. Alternatively, we have to come up with some innovative ways of how we can reuse the same space that we already have today. So Wi-Fi is already kind of at a breaking point. I mean, advertised rates versus actual throughput is only part of the problem. Years ago, when people were planning their wireless networks, they were focused primarily on coverage. And whilst coverage is really important, without wireless coverage, you don't really have a network. But you have to make sure that this coverage is usable, or as we refer to it, the quality of wireless. So I've seen this many times before. I've been out to site to investigate some kind of issue that's been caused by, or is happening on wireless networks. And the customer is showing me, full signal everywhere they walk with their test device. But in reality, there are so many other factors that can cause the actual quality of the wireless to be degraded, just because they can see the beacon itself. So this illustration really shows various radio technologies and client device traffic types, along with a number of clients, which actually dictates how much you can really get out of an access point in 20 megahertz channels. And in reality, you're never really going to achieve 100% airtime utilization. I mean, this is due to overheads in the wireless communication itself. So on average, you'd expect to see 75% to 80% utilization, and that's really kind of hitting the limit of what you would expect in a network in its current state. If you're doing any kind of voice over Wi-Fi, you need to really plan for at least 50% of clean airspace. And if you're looking at 50% utilization of a network to begin with, before adding voice over the top of it, then technically you're really going to overshoot what's really deliverable in terms of network connectivity and quality of wireless. Okay, so we've kind of looked at some of the issues in wireless today. So what does 802.11ax really bring to the table? So, I mean, let's kind of look at the headline figures, or the figures that every publication or news article will really focus on from the beginning. So headline figures, of course, the 10 gig Wi-Fi, or rather a theoretical top speed of 9.6 gigabits per second. Much larger capacity, technically 4 times in terms of capacity or density, coverage and performance, especially the performance at the cell boundary. It's estimated will be 4 times. This is on an 8x8 AP with multi-user MIMO in play. We also see an improvement on the smaller APs as well as a 4x4 access point, and that really depends on application or typical type of device that you use today. So 802.11ax also will be dual band, so it will utilize 2.4 gigahertz and 5 gigahertz bands, unlike its predecessor 802.11ac, which only operated in 5 gigahertz. And while many people have said that 2.4 gigahertz is too congested, it really has no future, 802.11ax will bring more efficiency into this band and be very helpful to devices with lower power requirements, like Internet of Things, where we'll see density of devices but without the real requirement for high bandwidth. So that's the headline speeds and needs and feeds. So let's take a look at, or a top level look at, the technology, or at least a major part of the technology that sits behind 802.11ax. So we've just briefly touched on 8x8 multi-user MIMO. The difference, or the biggest difference here, is that multi-user MIMO supports both downlink and uplink, unlike 802.11ac Wave 2, where it only supported downlink. So we have orthogonal frequency division multiple access, or OFDMA, which allows multiple users with varying bandwidths needs to be served simultaneously. Transmitting in smaller resource units, it also gives the ability to increase the range. But we must remember that 802.11ax focus is really about improving efficiency for density rather than coverage. We will briefly touch on OFDMA and how it works, as well as resource units as well. So like I said before, we'll touch on resource units in a moment, but from a very top level view, effectively allows a breakdown of the channel into smaller segments so that we can allocate to lots more devices in a smaller subset of existing channels. So really more efficiency in what we have today. So higher modulation rates from 256 QAM found in 802.11ac to 1024 QAM. And what this really means to everyday usage is that we increase the throughput available in the existing channel space versus what we had before. And the very top speeds, the headline speeds, will increase by about 40% over 802.11ac. So color coding has been introduced in 802.11ax for identifying overlapping basic service sets, or OBSS. Each AP is able to detect the BSS color identifier, which actually in reality is a numerical value. This is to determine if it belongs to the same BSS or if it can ignore it and transmit on the same channel. So this is based on thresholds that take into account the RSSI levels, the color code, etc. And the idea really is to try and address some of the challenges in co-channel interference so that devices can transmit despite the fact that there is something else on the channel rather than waiting. So finally, we have the TWT, or target wake-up time. It's another important resource scheduling feature supported by 802.11ax, and it allows devices to actually negotiate with the access point how often they will wake up and send or receive data. And this feature typically, we would see used in Internet of Things devices where they need to communicate ever so often, and rather than taking up resources from an access point, the device will be able to tell the access point that it's not going to check in until a certain time and then send and receive his data, rather than the access point allocating time or airtime to accommodate for this type of device. So let's take a high-level view of how some of the functions and features actually work in 802.11ax. So first, 802.11ax increases the number of subcarriers, which are also referred to as tones, on a 20 megahertz channel. This increases from 52 subcarriers, which we currently have today, to 256 subcarriers. 802.11ax also uses smaller resource units, which we refer to as RUs, for transmission, which will be able to increase efficiency over previous standards and allow the RUs to basically break down the channel and use or utilize more channel for different users. So resource units themselves can be sized in either the uplink or downlink and are allocated by the access point to accommodate application requirements. Resource units are often referred to as the subchannels, and you can have up to 9 users on each subchannel. The legacy clients, that's the non-802.11ax clients, will dramatically reduce the performance of your 802.11ax AP or network. This is because they don't really understand how the 20 megahertz channel has been broken down, or indeed how the resource units are even allocated. They will simply just use the full 20 megahertz channel the way that they've always been doing, the same way that 802.11ac has been doing and the previous standards before. When deploying 802.11ax, you'll need to explain to users, although they may be expecting great improvements from just upgrading the AP, it's not until that we have the client support that we'll really start to see the benefits of AX. And also, when mixing it with legacy technologies, we will start to see that impeding heavily on the performance. In today's standard, 802.11ac's frequency domain is built up of 20 megahertz channels, and to get more bandwidth, we simply add more of those channels together, so 40 and so on. But if a device is not utilizing the full width of a 20 megahertz channel, then we're wasting valuable resource. It's still consumed by every communication to and from a device, regardless of whether it is using the full channel or not. With OFDMA in 802.11ax, the channels are broken down even more so into smaller channels, which can be as small as 2 megahertz in width. The resource units are then scheduled by the access point and can be formatted on a per transmit opportunity basis for downlink and uplink. And then this can be also combined with uplink and downlink of multi-user MIMO to gain even more efficiency out of the existing channels that we already use today. Ultimately, this gives us much more dynamic control over the frequency, allowing us to serve clients with much more efficiently based on the application needs, rather than just allocating a full width of a channel, which is not always used. So that kind of concludes, from a very top level, 802.11ax. Obviously, there's a lot more to AX than we could cover today, but I want to end this session with a highlight of what do we think the challenges are for AX. So firstly, 802.11ax really requires AX clients for real benefits. While some improvements will be given to legacy clients, the majority of the improvements in terms of what AX standard stands for, with its efficiency and its density, will all really be gained from AX clients. So more capacity on each AP really means that the backbone network will be relied on to deliver that into the network and establish the connectivity throughout a network. So we'll start to see 2.5 gigabits per second and 5 gigabits per second switching being introduced as the norm when AX becomes mainstream. So another challenge is that we have more radios, we require more CPU processing power in order to accommodate for resource units, the calculations, the algorithms required, the color coding. All these types of functionality will rely and require much more power. So AX will probably, or majority of APs will require 802.3 BT or Ultra PoE, so up to 60 watts of power. So we'll start to see the requirement for that type of delivery as well. So there are some challenges with early releases of 802.11ax, apart from the fact that there's no AX clients. Some of the chipsets that are physically available lack the full functionality of OFDMA. They can't do both directions. And this certainly could provide some challenges when the clients start to appear in mainstream and really start to inhibit the functionality and performance that we could really gain from an 802.11ax access point. Thank you very much for joining this presentation. I hope that product changes, promotions, and also about up and coming technologies. Thank you very much.